Hello everyone, a very warm welcome to all of you to the Net Zero Energy Building Knowledge Series. We are very happy to have a lot of you attend this program. It shows that you are interested in learning about net zero, and we are very eager to get your feedback as well. So do, at the end of the session, give your feedback about the session and what else you would like to know in this knowledge series. This is a platform for industry experts to share their expertise, knowledge, showcase projects, technologies, and ideas to grow engagements for net zero energy buildings and really fuel discussions on energy efficiency at all levels. This program is supported by USAID's Market Integration and Transformation for Energy Efficiency program. You can know more about it on the website metri.edsglobal.com. I am Deepa. I am an architect and a green building consultant at Environmental Design Solutions, and I shall be the session moderator today. So today, as you can see on the screen, today's webinar presents a case study of an operational net zero building. The National University of Singapore's extension for the School of Design and Environment, called the SDE4, is thoughtfully designed to achieve the net zero energy goal. It is a 5-storied building. It's about 91,500 square feet in size, educational building located in Singapore. The building incorporates many innovative energy efficient features as you would expect in a net zero building. However, the most notable aspect of this project is the way the design team has approached thermal comfort. That to me is the key highlight about this project. It's not about providing comfort with the best available efficient technology, but really questioning the parameters of comfort. That has brought a paradigm shift in the way comfort needs to be approached for a tropical climate, while also achieving energy efficiency. So we are going to discuss about this and more in the webinar today. Giving you an in-depth view of this project is our expert speaker today, Wolfgang Kessling. He's joining us today from Stuttgart in Germany. It's about his lunchtime right now, but I guess he's fine and he is already probably done with it. So he is joining us from Stuttgart. Wolfgang is the director of Transsolar KlimaEngineering, an international climate engineering firm that approaches sustainability through innovative climate and energy concepts for buildings. He guided the design team of this SDE4 project from the inception to arrive at a building which demonstrates deep understanding of the tropical climate of Singapore. Wolfgang has been instrumental in spearheading energy concepts of prominent projects such as the Cooled Conservatories at Gardens by the Bay in Singapore, Zero Energy Office Building in Kuala Lumpur, Malaysia, and the Human Resources Headquarters at Novartis Basel in Switzerland. In this webinar, he shares his strategies, approach, and insights for the SDE4 projects. Before we move further, I just want to make an announcement that if you have questions about the presentation, please start sending in the chat box right away. Do not wait until the very last minute so that we can make most of the time available and we can take all of your questions. So without further ado, I welcome you, Wolfgang, in this webinar. Thank you so much for taking out the time. And I'm going to give you the controls and you can get started.
First of all, Deepa, thank you very much for this nice words and nice introduction. And a very warm greeting from actually Munich in Germany. And at the moment, many people would know this place better as the place where the Oktoberfest is happening. This big big beer festival, what we have in Munich in Germany, which is probably only 200 meters from here. So if there's some background noise, it is because of happy people celebrating in the streets. Thank you again for thank you again for your warm greetings, and let me extend my greetings from Germany to all the listeners and experts which are participating in this webinar from India and probably from other places, probably from Germany, also from the Academy of Transsolar. I'm one of the directors of Transsolar. We are based in Germany, in Stuttgart and Munich. We have a small office in New York, and we had an office in Paris. So we are in different European and North American places. Transsolar usually is involved in projects which are pushing the envelopes of creating comfortable spaces. We look into how can we create spaces which are extremely comfortable on the one hand side, and on the other hand side, using energy efficient technologies to bring down what this planet so urgently needs: energy consumption in the context of buildings, decarbonizing our operational energy demand for buildings, but we extend beyond that. We are interested in creating spaces and buildings which have a low carbon footprint, in line with what is today called the Agenda 2030 or the Agenda 2050. So that was a little and very short introduction. I welcome our guests listening to this webinar to visit our page to see more about the projects what we do internationally. This webinar, and thank you for this invitation, is about the School of Design SDE. It's a building number 4 of the National University of Singapore, dealing and giving a space for students studying architecture, studying design at the National University, a very well-known university throughout Southeast Asia, well known for the quality of education. And this particular place has been the alma mater of many architects emerging from there in Singapore. I would like to mention my team. Because a project like this, you are not doing of your own, you are always part of a bigger team. So let me start with the client who gave us the trust to work for them, which is the National University of Singapore, experts in designing building and still giving us, Transsolar and the other partners of the team, the trust to develop a building for them, which is their new and the future building where the students will be educated and the faculty will be working. I want to mention Siri Multiply Chris Lee, based in London and in Singapore, as the architect of this building. And there was a great team of architects of record and MEP coming from Sabana in Singapore. This is surely not an exhaustive list of people who have been involved and who have been part of the great success of this building. I apologize for those which I didn't mention. What was the vision? The vision of the client was very clear. Let's build a future building where we can educate the next generation of architects, the next generation of designers, and show how a high comfortable net zero energy building is a great place for working and for living, and is not something which is technically driven, which is awkward in design, but is just bringing a high aspiration and a vision together. So that was the vision when the architects, when the School of Design at NUS started, create a high comfort net zero energy building. So what is a net zero energy building? Let me start with this aspect. It's a building which has to produce its energy on its own footprint. I always say, don't borrow energy from your neighbor. Don't borrow energy from history. Today, we need to think in our own footprint and what can the footprint deliver as an energy to support and to run and to operate the entire building, which is a tricky one if you come to places which are vertical cities like Singapore. So let's do a quick cross-check to see what would a net zero building mean. A typical production on the roof in Singapore is something like 260 kilowatt hours per square meter per square meter and year. If I compare that with the average energy use intensity of an office in Singapore, which is something given as 252, we see this is 1-to-1. So in a traditional conventional energy demand world of 252 kilowatt hours per square meter in a year, one roof could only support one floor below. Now, if we want to extend that, we need definitely to look into an optimized building. So an optimized building with 70 kilowatt hours per square meter in year electrical energy use intensity then would allow that one roof could support 4 levels of a floor. That already shows the challenge. How do we get from 250 to 70 without giving up on quality, without giving up on thermal comfort, without making a very, very low quality building? And that was the challenge, how to do that. Let me start with the architectural idea. The architectural idea basically was, don't build a standard form, a box, a closed box. No, open something to the beautiful tropical environment. Open up the facade, open up the box form, let cross ventilation work, let the flow of outside air go through the building. The next idea was, let's shade this building from the extensive sun by an oversailing roof, and then use exactly this same roof for renewable energy production. So far, that is a kind, simple idea, and everybody would agree that is probably following very basic rules to design a building, but it was quite a challenge. I go through this challenge in the design a little bit later, but I don't want to be and then wait too long with beautiful images, because this building is built and it works, and let's have a look on how beautifully the building is integrated into the tropical environment of Singapore, a city in the garden, as Singapore calls himself, with a lot of biophilia. You see open spaces. This is a terrace on the, I think, the 3rd floor or the 2nd floor, where the students can gather. They even, during the design process, took a lot of attention to keep biophilia, to keep these beautiful trees alive, to support that the vegetation is staying alive and creating this building. You see the oversailing roof with the face facing the south. We see the facade on the east facade, that lady standing in the shade of the east facade panels which shade the east facade. This is another view into the open spaces and the escalators. I'm just going through some views. This is the internal auditorium, quite open and inviting. And this is one of the seminar spaces. And I will come later to more aspects of the seminar spaces. But these are the spaces where most of the students and the faculty spend most of the time in this building. So it was very important for us to design these spaces right, because this is where people need to learn, where people need to be fresh in their mind, where air quality needs to be good, where daylight quality needs to be good, where acoustic and thermal comfort needs to be good. And we spent a lot of focus on making these places right. And here's some other images from showing studio time. The studios are long connected. On the left-hand side, we see the south facade. What we also see is the anti-glare and shading devices on the upper part, which redirect daylight into the deeper part of this, the building. We see the acoustic panels. And if you see my mouse, I try to use it. You probably can notice where fans are hanging down in the ceiling, and they are equally distributed across this entire space to support thermal comfort. I will come to this in a second. I love how students picked up the space and started opening the facade by themselves, pulling and using the internal devices for the glare, and sticking sticky notes on the facades. This is the view from inside, and that's probably the last image I show from outside, showing this entire building, looking onto the south facade of the building. So let me come to the question of comfort, and Deepa already mentioned that this was a kind of driver, and right, we would also use the word paradigm shift in terms of comfort design, because that was really making up a lot of our time, talking about how do we create spaces which are looking good. Let me quickly introduce into the climate of Singapore. That's quickly done. The red line is the temperature, the green line is the humidity. It's a very, let me use the word, boring climate, 25 degrees lowest, 30, 33 degrees highest. There's no winter, no summer. We are at the equator, so we have always kind of temperature in the range I indicated, but always a very high humidity ratio. And let me also bring attention to this slide, what is coming up in a second at your side, which is by the famous founder of Singapore, Lee Kuan Yew. And he's well known for one quote, which I'm reading here. Air conditioning was the most important invention for us, so for Singapore. Without air conditioning, you can work only in the cool early morning hours or at dusk. The first thing I did upon becoming Prime Minister was to install air conditioners in buildings. This was key to public efficiency. So the founder, even the founder of Singapore, is well known for his quote that air conditioning is related to, let me extend a little bit what he's saying, the performance, and that air conditioning is important for Singapore. You can disagree with what he says, he can agree with what he says. Basically, what I'm seeing here and what I'm usually giving as an understanding of my side, he understood very early that comfort is important for people. Only people feeling themselves in comfortable conditions, only people feeling themselves in their comfort envelope can perform well. At the time when he made his quote, comfort was similar and synonymous with air conditioning systems. Today we know better. 25 years we know way better that thermal comfort has many aspects, and what I'm talking now will deal with this, that it's possible to create what he was urgently looking for his people, comfort, in a different way. Well, his quote actually is probably good to understand in the context of this image, was from an installation of Rem Koolhaas in the Venice Biennale 2014. And it shows, and if I use my mouse again, it shows the space we are usually occupying, the space underneath a false ceiling. And on top of the false ceiling, there is many ducts supplying fresh air, returning fresh air, return air to air conditioning systems. And typically these spaces on top of the false ceiling in Singapore, they can make up to 1.8 meters. They would be higher than myself. I could walk into these spaces. That's a tremendous waste of space just to air conditioning a space below and keep this cool and keep this dehumidified. But we became used to this. So let me challenge this. Let me challenge what is really comfort and how can comfort be created, and quickly jump into something which we now will go through in this ongoing webinar. So if the conventional approach of comfort is to reduce what is called the operative temperature to 24 degrees, our approach is, let's challenge this and let's talk about an adaptive comfort approach where we allow operative temperatures of 29 degrees. And I can hear many people saying this is crazy, 29 degrees, but combine these temperatures with temperate air setting and elevated airspeed. And let me share something why I think this is important, because if you look into a chart you can create with the CBE, a Center of Built Environment tool of the University of Berkeley, which is available for free and online in the internet. You can use that tool to just quickly cross-check what is comfort and what is not comfort. So you can key in temperatures for air of mean radiant temperature, which gives the operative temperature. You can key in airspeed, you can key in humidity, metabolic rate, and clothing level, and you would get a psychromatic chart indicating a blue envelope of comfort and a red dot which is representing the indicated environmental conditions, saying, wow, that is obviously not comfortable. And how is that rated? That is rated with two parameters I would like to reintroduce. I'm sure many of you know these parameters, which is the PMV, which is standing for predicted mean vote, and the SET, which is standing for standard effective temperature. So the predicted mean vote, if this is comfortable, should be in the range of plus minus 0.5. Obviously, we are way higher than plus 0.5. That's why it's red, why it's indicating discomfort. The standard effective temperature, I come back to back in a second, but that should be, let me say, in the range of maximum 27. Now, using this tool, what happens if we change the setting for airspeed? If we change the setting of the airspeed to 0.7, a gentle breeze, I go back and I go 4, and you see the comfortable envelope now is wrapping around the environmental conditions we are evaluating, and that is indicated by the predicted mean vote with elevated airspeed. It's now 0.3, and the standard effective temperature, which is now 26, indicating, wow, even at crazy 29 degrees operative temperature, this would feel perfect, this would feel comfortable. And bringing that in one slide into a bigger context, when we design buildings, we shall leave the common grounds of designing for air temperature only. Humans are sensors, and humans react to a variety of environmental parameters, which include the dominating parameters indicated on the left-hand side: mean radiant temperature, air velocity, air humidity, air temperature. It includes my activity level and it includes my clothing. If I am respecting all these parameters, I have a way better understanding. Of what is creating comfort, and I can model this comfort through predicted mean vote. And I repeat what I just said, indicating between plus minus 0.5 is the perfect comfort we can create, and that stands in the conditions for Singapore, tropical conditions, for something similar to maximum 27 degrees standard effective temperature, maximum and minimum 23. So now, if you want to design a building in a more holistic way and talk about comfort in a more holistic way, we need to leave the ground of air temperature, expand the parameters. And if this looks like complicated, I would disagree. It gives designers more opportunities to design comfortable spaces. And it gives designers particularly more opportunities if you're back showing this climate data from Singapore, thinking about if the red indicates the air temperature, the green indicates what feels comfortable if people's body is exposed to air movement, to a gentle breeze. And you see the interesting and actually excellent overlap of the green, the adaptive range, with the temperature range back in red. So to bring that forward, we have been introducing the idea, and we said, okay, let's then make a comparison between full AC, simple design versus adaptive design. So let's think about how we can bring things together from the both worlds. And I have a very simple comparison. On the left-hand side, you see the full AC, a typical conventional design, fresh air supplied with heat recovery, which is not typical for Singapore, but we wanted to say, let's do it as efficient as Swiss people, for instance, would do it. We have a return air cooling. We have a large false ceiling because it needs to cover. And to take up all these systems, we lose a substantial space in the false ceiling, and we need a closed facade because this building needs to be sealed and needs to be closed because of the air conditioning. Comparing that to an adaptive comfort, what we designed for the School of Design, we don't have any false ceiling anymore. We supply the same fresh air amount. We use ceiling fans to move and elevate the airspeed in the space. We have no return air system. We have just spilling over the air back to the corridors, and window opening is possible. Here are some more details. Basically, I want to highlight that between the full AC and the adaptive comfort, we spend a lot of emphasis on supplying the same fresh air amount for people, which is in the range of 35 cubic meters per person. So we did not give up on air quality on a low carbon level in the spaces, because this is where I would really give up on indoor air quality. So both systems, full AC and adaptive comfort, would be designed to deliver the same air quality. They would, having said that, designed to deliver different temperatures. And how would they perform different? How would they create these conditions different? Let me start with the air conditioning system, the full AC. And in this diagram, we see 3 days. We see indicated the air temperature, and we see indicated the mean radiant temperature. So during the daytime, that creates an operative temperature between the radiant and the air temperature of 25. We have a low humidity ratio in the day, and that creates, indicated by the red line, predicted mean votes in this specified range of highest comfort. This is how typically air conditioning systems are designed. And this is where we started challenging ourselves. Can we do that different? Do we need, is that the only way to do it? And looking on an adaptive comfort design, you already see by how the graph changes, operative temperature is 29 degrees. Radiant temperature is even higher. Air temperature is in the range of 28. Humidity level in the space is higher, but now with an elevated airspeed, with a gentle breeze, the red line indicating predicted mean vote is creating comfortable conditions for humans, for the visitors, for the people who are using the building. This is what matters. This is what matters to them, creating comfort and what is important for them. It doesn't really matter how comfort is created. It's important that we create comfort. And I have 2 more charts indicating why we do what we do. This is a psychromatic chart showing the ambient conditions of Singapore as a gray dotted cloud in a psychromatic chart. And this is what typically in this bold black box, what ARCHI indicates as conditions. And if you condition a space with a tight air conditioning systems, where I move the mouse would be the conditions in the space. So it's 26, probably 26 degrees, and it's a low humidity. Excellent comfort indicated by this green bar down here. So all points are within predicted mean vote range, which is comfortable. Energy is high for cooling and for dehumidification of the air. Classical, conventional AC comfort. What if we do it with adaptive temperate comfort? And in the psychromatic chart coming up at your screen, you see now in an adaptive world, temperatures are higher, which is the green. Humidity is higher, which is indicated by the relative humidity or by the absolute humidity ratio on the y-axis. Still, if I evaluate this in terms of comfort, taking my holistic approach of the 6 parameters I introduced before, 98% of that time is rated as comfortable. Energy is really going down. So we don't give up on comfort. We don't give up on what we design primarily for. We design for people. We design different with this adaptive comfort, adaptive temperate comfort approach. But the benefit is way lesser systems, way cheaper systems, no return air system, no false ceiling, and way lesser energy. And that is summarized in the chart, which is coming at the moment. So bringing down from full AC, you can bring down in the range of 36 to 56. So we usually say in the range of 50%, you can bring down energy demand by a tremendous saving and investment cost without giving up on comfort. Does adaptive comfort work? A few words on that, because we have been really challenged in Singapore, in the world where air conditioning is so embraced everywhere, from taxi to private to public buildings. Does adaptive comfort work? And we had the chance, and we have been invited by the United World College in Singapore, which we are very grateful for, from the entire team. They supported us by changing in one part of their building for 3 floors, for several spaces where children have been studying, so in the school, they changed the internal conditions to what we are suggesting, where we have been suggesting to the NUS as the right conditions. So they increased the temperature, they increased humidity, they let the building come up in temperatures, and we increased elevated airspeed. We could use their ceiling fans and we could use Dyson fans. And these images show how we had our instruments right next to the children, to the teacher, to say, to find out what is the thermal conditions in this space. And we took, it was about a 1 week measurement, and we took measurements about the carbon level until the point that we said, okay, now let's invite the faculty members, let's invite NUS, let's invite the future user from the faculty side to spend time in this space. And I need to emphasize on this. If you want to think about how you perceive a space, if you think about, is a space good, does it feel comfortable, you need to spend time in this space. You need to extend your time in this space beyond minimum the 20 minutes you need to adapt from your body to the new conditions. So we spent more than 2 hours walking around, talking, seeing through the window, talking about the comfort and seeing the instruments, until we came to the point where we asked ourselves, does it feel good? Does it feel comfortable? And we all agreed with the dean, with the faculty members, all experts in their field of architecture, of air conditioning systems, of comfort, and we agreed, yeah, it feels good. And then we looked again on our measurement device and we found, okay, that's a quite higher air temperature. And that's a kind compensated by the ceiling fans, which makes us feeling by the gentle breeze that is good, that's comfortable. So that was key to make this effort with our client to go through this kind of exercise, to make an informed decision, which is not on paper, which is not on theory, which is not using internet tools, which was based on what is our personal body perception saying. Does it feel good? And if so, that created the background of the decision that we went for this adaptive comfort. This somehow concludes a little bit how we created and seeded that people trusted in this, and how we could start in doing a thermal zoning of the building. So we have opened up the facade, as you already have seen. We have reduced full AC spaces to a minimum of 17%. And I need to say something for this. I was actually pushing for that the library, and the library is air conditioned, that we have spaces which are air conditioned. In particular, in the context with stressful situations with the students, I suggested, let's don't go too far. Let's have we have energy. Let's still have spaces which create comfort in a different way, so that people can make their adaptive choice. They can go to the natural ventilated when they want. They can go to the full AC when they want, but they can also spend in the hyper-temperate spaces, they can spend the time. And there's about 10% of spaces for mechanical space. So that informed process, going through intensive analysis of theory up to the point of an experimental exposure ourselves, that made so much background and that seeded so much confidence that the client was quite clear in designing and accepting that this is bringing forward his new school and putting it on a page in terms of a really paradigm shifting design for comfort. One last slide about that. It shows technical things. So there was always this human-centered design, but we also spent a lot of time informing our MEP engineers, minimum bending of ducts, minimized duct work, very efficient sizing of systems, all things to reduce what is usually annoying, noise of air conditioning system, and what is less annoying but not good for a net zero energy building, high energy demand for air conditioning systems and moving air around. So we spent also a lot of emphasis on this. We also spent a lot of emphasis on the facade, which I'm going a little bit quicker. So we looked on other qualities, which are very important for our spaces. So we made intensive daylight modeling. This is one of these long studios. You just have seen the images. We spent a lot of time saying, how can we make a facade as efficient that it's in a tropical context, good for thermal, but also good for daylight comfort. And we looked on parameters which are the daylight autonomy, and we looked on parameters which indicate what time and how much time and how many spaces are in good condition. So let's say a useful daylight index in the range of 300 to 2000. What facade elements receive too much and what areas receive less? And this is the areas where we put the coding studios, the MakerBot studios, places which way less depend on daylight. We did intensive studies and just show one sketch about what kind of combinations of overhang, but also other combinations, external shading, internal blinds on the lower part, on the upper part with redirection, combination with external shading, until we came to a point where we could say, now we found an optimized facade. But what would qualify an optimized facade? It was that we extended the typical range and saying, okay, an optimized facade should have a low glare potential. It should be a facade which increases the spatial daylight autonomy. And usually when these parameters go high, thermal comfort goes low. So we have been looking for combinations where in all these three different categories, we are getting as green as possible. And you see by the chosen variant, which is with a slight overhang, with a kind of redirection system and blinds which are only temporarily in use, we choose that system for the facade design. You already see that in these many options, there is a process which is key. And at Transsolar, since our early beginnings more than 25 years ago, we talk about that process. We need to break a linear process into a process which is an integral process, which allows to target the individual stakeholders, because we need to go at the end through three major steps, and we cannot do that without getting everybody involved. The first step, obviously, is to engage with the client and the architects to minimize use intensity. But this is not only through building material, this is not only through high efficient system. This includes client being challenged and saying, do I need this system? Do I need this kind of, do I want to use this kind of laptops or machines in my building, or can I go for more efficient systems? Do I need this big allowance for internal loads, increasing my allowance for air conditioning systems? So it was the client plays, that's what I want to say, a major role in this. And then once this is really sorted out, MEP and engineers can minimize energy use intensity by optimized technical systems. And if you only have done your homework in these both steps, you can get to maximize use of renewable energy of your site. This all includes that kind of integral design process where you always challenge your design. You go through analysis, you learn something, you say, oh, we are not good, we need to do it again. And this kind of informed process, this kind of scientific informed process was key to develop with everybody in the team the understanding how we would get from our vision to the building as it is built and as it functioning. Deepa.
Yes, it's a little time for a quiz, but really we wanted to, just take a moment and kind of interact with the audience, and it's been really great information from you, Wolfgang. Operative temperature at 29 and getting the clients to buy that, and having the ceiling fans in is no small thing, and it indeed is a paradigm shift. We as consultants also face this challenge day in and day out, and this is commendable. So we thought, we can have a little quiz and make sure that everyone, all the audience, we are on the same page as far as what we're talking about. Are we clear on what comfort is? Adaptive comfort, elevated airspeed, higher operative temperature, a lot of things being discussed. So just a little fun thing, and also kind of, tying into what we've been talking about. So here is one question that will come up on your screen, and we will, and 1 second, just give me 1 second, adaptive comfort, right. So here is a little poll that's on everyone's screen, and you can now select the right answer, and we can get in the votes. So question is, adaptive comfort allows for what of the following options? Higher air speeds, higher operative temperature, opening building windows, or all of the above. This has been a key thing in the SDE4 project, and they've achieved a lot of these things. I don't want to give out the answer. So the votes are coming in. I'll wait for a couple more seconds. All right, so 89% of the audience, oops, it reduced. 80% of them are saying all of the above. 6% are saying higher airspeed, 9% operative temperature, and the rest opening building windows. Okay, I thought there won't be any takers for the rest of the options, but clearly the majority of the answer is correct. Majority of you have got it. All of the above. Adaptive comfort does allow all of the higher airspeed and hence higher operative temperature, and of course opening building windows when the weather is great outside. And using all of the strategies, clearly what we've understood in the presentation is that the electrical demand has been reduced significantly, and that actually brings me to the next question, because here everyone got the answer, so I guess we can move on for the next question. Is, yep, this is the one. So in this project, using elevated airspeed and higher operative temperature, the electrical energy could be reduced by what percentage? 20, 30, 50, 70? If you could recall what we just discussed. The point of this question is not to have like a recall, but for you to just understand that what is the magnitude of reduction that could be achieved. And if you're not able to recall, then you should be able to take your best guess of what is the potential that it holds. So waiting for a couple more seconds, please put in your votes. Even if you're not sure, just take your best guess. That's the way we could actually have a fruitful discussion. All right, so we have the votes now. 60% of the people say it's 50% energy, electrical reduction. 20% is 30, and 23% of the people are saying 30%, and there are some votes for 20 and 70 as well. So clearly everyone's paying attention. So yes, it's actually more than 50% of electrical energy reduction, which was possible in this project with the kind of approach that has been taken by the design team. So Wolfgang, is one quick thing. The architects and did the buy-in of having this higher operative temperature, was it easy with the architects?
The answer was yes. Chris Lee, I think he is from Singapore or Malaysia. He was born in the tropics, and he was kind of clear in this climate that an approach which allows for engaging systems to create breeze is the right thing to do in the tropics. So he was quite clear in this, and he was very open to to rethink his facade design, to rethink the function of his facade in terms of exactly achieving what was in his mind. He was talking about a building which opens up, and he was very open from his and supportive from his design to say, okay, let's create a performing facade which does what you just said in the context of the quiz, open up for ventilation whenever people want to do that and want to allow that, and bringing temperature high actually to 29 degrees. As you have seen the range, if you can see my hand, brings indoor temperatures into the range of outdoor temperatures, which is the moment when you say open your facade.
That's right. So it does. So the users have to be active so that they engage, and they are also, engaging in the whole adaptive comfort process. All right. So I don't want to keep you from the rest of your really engaging presentation. So let's move on and with the presentation. And just a moment, I want to again reiterate to everyone who's listening in, if you have any questions, please put it in the chat box and we can start taking it towards the end of the session. And so every time we get a feedback that my question wasn't taken, so we don't want that to happen. We want all the questions to be answered. So the sooner you do it, the better it is. Yeah.
So thank you very much, Deepa, for these questions and somehow quickly digesting exactly the essence of this first part. The second part is a little bit shorter and is actually bringing me to two things, which is the net energy story, which somehow happened to Transsolar, to my team and to all the experts, but at the end turned out to be the most helpful tool to get everybody engaged. So we called it the net energy story. What I learned from this is that I typically since then try to implement a net energy story as a kind of process in the buildings we are involved with, because it turned out to be such a powerful element and tool. So let me start this net energy story with what is the available at the site. So what is actually the quality of the site? And if we have a roof extending over the building, what we quickly learned is that the optimized photovoltaic production on the roof will give us something like 500 megawatt hours per year maximum. And setting that in context with the typical energy, sorry, I just lost something. Setting that in context with what is typically the energy demand of a reference building, and you should see a slide now showing the energy demand of a reference building, you immediately see there is a huge gap between what we produce in green to what a reference building in Singapore would need. So that was the starting point, and everybody was scratching his head and saying, so what the heck is possible to do? So what can we do? And that was the moment when Transsolar came onto the project and started to engage with everybody. But everybody, and I need to repeat that, everybody had a role to be supportive here. So what we did is actually we challenged a part of the client's brief saying, is that really what you need in your building? Is that really making a great university building? Is that really energy what you want to spend, and space is what you spend on the roof? So basically we clarified, take maximum space on the roof, don't give up for anything else which is compromising your PV production. And then we started looking into the different elements we typically look to. You are designers, you are architects, so let's start to look into an optimized building. So an optimized building definitely would bring down energy demand. Sorry for this. Would bring down energy demand, but it's not sufficient. Then we started, okay, let's do something crazy. Let's think about the most energy efficient system you would buy, let me use the word again, in Switzerland, with heat recovery, with latent and sensible heat recovery, and would that work? We found out even if we would have gold in our pockets, a high efficient AC system would not help us to achieve on the 5 floors of the building what we need to do. So we started more and more challenging what can we do, and we have been thinking about that hybrid system and the temperate approach. So we have been thinking about, can we introduce this new thinking, that paradigm shift in creating comfort inside? And the question to my team was, can we design on purpose for this? So how to design on that? How do we design? How do we use the simulation tools? How do we use the typical tools and classical tools we have to design for that? We went through very many details. We optimized very many spaces. So we went more and more in details of different spaces, saying, can you bring down light? Can you bring down plug door? What is auxiliary driving? What is the mechanical ventilation? What is really required? Can we do that locally different with fan coil units? Can we? And that was a step-by-step process which we have been going through actually in 7 design charrettes, where we always have been working with all the different stakeholders and then summarizing the aspects, going back to Singapore, having a 2 or 3 day design charrette. We went through the things and we signed it off until we came to the point that in optimized design, in the end of this process, we could show we can achieve this amazing building, this amazing comfort. We don't compromise on the use. We have all the program areas considered, which are super important for that building. So we went through this, and that informed actually very much our entire design team about its own role. So what is to be contributed by an efficient mechanical design? What is to be contributed by, let me say, the PV design? So we really have been talking to the different companies, potential companies installing the PV system. What, if you would do the best system on the roof, could be your contribution to the success of this building? So there have been many fathers and mothers of the success. And in summary, the new school of design at UNOS is a university building in the tropics, which is extensively using temperate air and elevated airspeed, which creates highly comfortable spaces, which is energy efficient, low in investment cost, and is 100% powered by photovoltaic on its own footprint. And I think that is an amazing success for everybody who has been involved. The building is running and up and running since January this year, 2019. It is quite well received from everybody working there, from the students now having their studies there and their starting their academic career at this place. And what it makes it kind of important for me is people who grow up, who have the opportunity to grow up, to study and to start their career in such a building. They know that buildings like this work. They know that buildings like this can be constructed, and this is not a way back into old world of no comfort. It is a way forward, and it's exactly targeting on what this planet urgently needs today to create comfortable spaces with least amount of embedded and used carbon for operation. Let me zoom out for a second and have give me 2 or 3 minutes, because I want to relate it to the bigger picture, because to share why I think that's super important. At the moment, we have about 194 cities with more than 1 million people living in Asia, and you can read the numbers for the Americas, for Europe, for Africa, and Oceania. And what we know is that since 2010, and we are already to 2030, so we kind half through that period, another 84 billion square meters will be built on this planet. This number says nothing. Let me set that number in context. This number is similar and is equivalent to 3.5 times of the built infrastructure of North America, or something like 7 times a year Hong Kong. That is tremendous numbers, what we are going to build, and we are already through that process. And all what is going to be built is mostly happening in Asia. And you see, if you go through this slide, that about 9% is going to be built. Roughly 10% out of that is going to be built in India. So we really need to challenge, what are we going to build? Most of that 60% will be built in hot and humid climates. And that brings me to my closing remarks. The way how we design buildings is super important. These are images from friends of us, Morphogenesis, and this image shows building across India, across 5 different climatic zones in India. And what you don't see is any context to the climate of these buildings. They all look like a copy from downtown Chicago. So it's extremely important that we design buildings which suit the climate. But in the similar way, it's extremely important that we understand what is comfort. Comfort in moderate climates, comfort in tropical climates, comfort in mixed climates. It's quite different. What is understood and what is perceived of comfort is quite different. So we really need to challenge the way how we understand comfort and how we design for comfort. We need to get out of the trap understanding that air temperature is describing thermal comfort. And when we do the right architecture, when we do the right way of comfort, it has a significant impact, because buildings in the tropics designed for adaptive comfort reduce at minimum 50% less energy. And this is where I want to close my presentation. Thank you very much for all the time you spent with me, and I give back to Deepa. Probably you have some questions.
Yes, thank you so much, Wolfgang. That was a great presentation, and you really really hit the bullseye. Like, we really need to challenge, does air temperature really define comfort? We need to question these things. And when you were citing the example of Singapore, where you actually question, do we need to have so many computers? Do we need to have X and Y things in the building? That actually addresses the subject of sufficiency at many levels. And that's a very important topic. Sometimes we tend to not discuss much, but it is again an important thing to know. What is sufficiency in the context of energy and comfort, and what is appropriate in the climates that we live in? And hence, climate responsive design is all the more appropriate and high time that we design buildings which are climate responsive and look like they belong to that environment where they are built. So thank you so much for that presentation. Yes, we do have a lot of questions, and I'm going to start taking in one by one. So the first question is, was a post-occupancy thermal comfort or similar survey conducted for the SDE4?
There is a post-occupancy survey of comfort. The building, the NUS and the School of Design itself understand their building as a research building also. So they have a lot of sensors on the one hand side to trace the climatic environmental conditions. On the other side, they make surveys, they talk to the students in different ways. I probably don't collect everything of them, but there are sensors attached. Some people wear sensors around their arms, and they can answer questions by tapping on that. Does that feel good or bad? But there are also more detailed questions asked to people getting into one of the aspects like air quality or thermal comfort. And this is done by the NUS themselves, and part of that already had started to become published, and they will publish extensively on that, because I think what this question indicates too is there is a tremendous demand for qualified feedback beyond what was the design intent.
Okay. Next question, how did you ensure that the increased air velocity did not induce uncomfortable air drafts in the occupied space?
That's a quite good question, and that opens up, from my point of view, that is opening up the question on how much do designers today know about designing with breeze, designing with elevated airspeed. Basically, there are simple answers and very complex answers. Basically, draft is usually only in context with low air temperatures. So drafty situations, as we typically understand them, is because a chilly air conditioning system is blowing chilly air onto people. So cold air with too high airspeed. This is not happening in an environment where we have designed for temperate air, and already the supply, the gentle supply air is warm enough to not create discomfort. When it comes to the question of what airspeed is right, we learn that, let me say, everything below 0.8, 0.7 meters per second breeze in a space is very much appreciated by people. When it comes to airspeeds beyond 1.2 meters, people start seeing that something is moving, or the hair is shivering, or even papers start flying around. This is where we definitely don't want to go. We always suggest to stay below 1 meter and to hand control to people in two regards. Move your space, move your table, move your chair to a position which is good and you feel comfortable. And second, switch on or switch off the fan which is affecting your comfort.
Right. Next question. If temperatures are increasing due to climate change, what will be the impact on comfort? Was this considered in the design?
I think that's an excellent question. It's about the resiliency of buildings. Basically, we consider that this building is a very resilient building. Even if power fails, the embedded autonomy in daylight, the embedded autonomy in fresh air supply through the facade, the embedded autonomy that this building can keep people, and people can stay without any power in this building, from my point of view, is a big benefit of the design. So resiliency is always on the table when we design buildings, and is always important for us. The way to use elevated airspeed actually is very good, going in parallel with what I just said. Even if the chiller, if the temperate air supply wouldn't work and the windows would stay open, the fans would create comfort, and a 1 degree increase in peak temperature would be easily compensated by this air movement.
Right. Next question. Is the net zero concept, like similar process that you just mentioned, applicable to retrofits as well? Have you tried that?
That's a good question. I'm not aware of. I'm aware of many net zero buildings, small and in bigger size, but not aware of a retrofit. Probably I'm wrong, but at the moment I wouldn't recall it. The process would, from my point of view, be kind of similar. You challenge what is the program you want to use the building for. You challenge, for instance, if it's a school, how can you create spaces? How can you improve the facade? How can you improve these elements which are important for the design? And at the same moment, you balance it out versus your roof and your availability of renewable energy at the site. And I would always start with this. I always engage my team first with this question: what is what I can harvest, and what is what I most likely will use, and how do they stand in which context, giving me a feeling for, can we push the limit, can we do it, or are we out of range? Just one simple thing. Usually in the context of net zero buildings with electrical energy, we say it needs to be somehow in the range of 4 or 5 levels. So retrofitting a high-rise wouldn't work, just because of the limited availability of roof and facade areas to produce renewable energy. I hope that somehow answers the question.
Right. Next question is, was outdoor thermal comfort or air comfort also considered for the project?
Outdoor comfort is quite important for us. It was no design driver, besides of looking that areas can be shaded by the roof and are very open for cross ventilation. additional system, as my team of Transsolar is working on, let me mention, dry system have not been considered in the context of this building. But I'm very interested usually that the buildings themselves are not dropped gems in a context, that they are somehow connected to indoor and outdoor. In particular, if you have such a beautiful vegetated surroundings, they should always be understood as part of the surrounding, which means be careful in designing spaces where people can use outdoor spaces and benefit from this beautiful surroundings.
Right. Another question, can you elaborate on the kind of instruments used during the adaptive comfort experiment at the World School?
Basically, what you need to measure is the 6 parameters, what I mentioned in my talk, which, let me start with the easy one, which is the air temperature and the humidity. So we had sensors for air temperature and humidity. We had sensors for the mean radiant environment, which is something like a globe sensor. We have been using sensors which can read the mean radiant temperature in a space and kind of have a similar coating and color like a typical clothing of a person. And the fourth parameter, what you need to measure is the air movement, so the air speed. So we had sensors which we carefully placed them so that they could pick up the prevailing breeze in the space. And besides that, measuring this, you always need to observe people and say they have this kind of activity and this kind of clothing so that you can create the full picture. So we need to measure the signals, what I just, and the parameters I just explained, and observe people for the parameters which are hard to measure to make the full picture.
Right. And now we would just take the last question. Oftentimes, CLO value do have an impact on the comfort parameters. And you know, in typical office buildings, people dress a little differently. For this project, was that discussed, and was that a decision or some sort of a stand taken that the average flow value of occupants in this building would be this, so that they are more, you know, they perceive the adaptive comfort better?
That was discussed indeed, and we had some fun experiments with a whole group of students, a whole class of students I was teaching when we discussed that in Singapore, finding out that there have been people with very little clothing factor, technically speaking, and others who had still their hoods on, and they have both been in the same space. I usually say it like this: clothing is an excellent adaptive choice for people to adapt to a situation. So I can adapt my clothing, I can wear a pullover, I can close a jacket, or I can take a jacket off and I can wear less. So I always suggested to leave the classical thinking that there's a fixed clothing. Buildings of the future and workspaces of the future and spaces and how we use spaces in the future will probably allow for a more flexible clothing, which helps people in a very traditional way to adapt to the conditions in which they find themselves. And probably an interesting story, for the opening ceremony of this building, we had been in the upper floor, and I was bringing a jacket because I was just, let me say, thinking of, oh, what happens if somebody wants to make an interview with me, and shall I use a jacket and should I bring a jacket, things like this. So I even increased my clothing factor, and I was good for 2 hours in this space. Clothing factor actually represents the variety of human response and people, and this, we should walk into a world, into a future where we allow for more flexibility here.
Absolutely. I think that's a great note on which we can close the webinar, that this is how it needs to be: flexibility for people and the buildings, both. And that's the, that's the way forward to increase resilience and build a better future. Thank you so much, Wolfgang, for your time and for wonderful presentation, for answering all the questions. And I hope we're not keeping you away from your lunch too much. So, and with that, I have a few things before we end the webinar today, a few announcements and a few things that we're doing. We have the NZEP tours coming up, the two buildings, Sierra E-Facility and the Infosys Hyderabad, and stay tuned for the dates when we will announce it. And then we also have, as you know, several online courses on great topics that will allow you to learn more about building design. And here is one course on daylighting, very simple to understand and follow. Use this code to access this course for free. Subscribe to our monthly newsletter, the NZEP Times, for all the activities and initiatives and things that we are doing, and for everything that you want to know about NZEP. Sign up today on our website, get connected with us through our NZEP portal. Here is the web link, and connect with us on social media for all the other updates. And do let us know in your feedback what other content you would like to see on the webinar, and we'll try to bring that to you. With that, just want to say have a very good weekend, and thank you so much for your time and attention. Thank you so much, Wolfgang. I wish you also a great weekend.
Thank you very much.